Class of number theory. So what we're going to do today is we're going to get up to Fermat's little theorem. So how many of you have heard of Fermat's little theorem before? Okay. So how many of you have taken abstract algebra? Okay. So this is unfortunately one of the places where there is a huge overlap between them. Is there anybody here who has not heard of Fermat's little theorem? Everybody's heard of Fermat's little theorem. Everybody's comfortable with ClockArithmFlT. Okay, this is nice. We're going to go through this at warp speed. Okay, if you want to slow me down, please slow me down. Did I tell you the clicker story from when I taught differential equations? This was the linear algebra. Did they want a review of 2x2 matrices? And nobody wanted a review. Nobody was willing to raise their hand. But 43% of the class, when I used clickers, said they wanted a review of 2x2 matrices and differential equations. So if there is a question you have, almost surely somebody else has that question too. They will never publicly thank you or even privately thank you. Nobody got it? Excellent. Yeah. That one? Yeah. Okay. So, yeah, don't make value judgments on him. Okay. So, we did ClockArithmFlT last time. And part of this is just to make sure we all have the same notation. So we say x is congruent to y mod n if x minus y is a multiple of n. We might, we might write 3 bar as the equivalence class of 3. And frequently in a situation like this, it should be clear what n is. So for example, if n equals 12, then 3 bar would be ... -9, 3, 15, ... It'd be that string of numbers. And the whole point of equivalence is for a lot of things, only certain properties matter. A lot of times it only matters is the remainder when you divide by n. How many of you know Galileo's famous experiment from the Leaning Tower of Pisa, where he drops 2 spheres to show that the mass of the sphere does not really matter, they all fall at the same speed? How many of you have heard of this experiment? Excellent. What color were the spheres?
Orange and purple.
No, but close.
Black, I think.
Right? Why does history not know the color? Your sketch artists were really bad back then, didn't have enough time to draw things. Didn't matter. Maybe if one sphere was white and one sphere was black and they'd been sitting out in the sun for hours and it was a really hot day and the materials would be at different temperatures, maybe if they're at different temperatures as they fall, that could cause an effect. But for the most part, they were probably kept in the shade, brought out, doesn't really matter. So the equivalence class would be the color would not really matter, and we would want to remove that property. That's how you should view equivalence relations. These are reflexive, symmetric, transitive relations, often. And the point is, it helps us focus on the properties that really matter. So we might use, z mod nz is going to be a set of representatives. Typically, I would like to write it as 0, 1, 2, all the way up to n minus 1. You could choose other representatives, of course, but I think this is a good set to work with. We're mathematicians, we like to start counting with 0. And then you can start asking what kind of properties do these numbers have. So you could add 2 numbers. Now, unfortunately, if you look at a clock, if you do 10 plus 5, 10 and 5 would both be in here, but they would break the bank. But you say, well, I have to add modulo 12. So 10 plus 5 is 15. I throw away as many 12s as I can, and I would now get 3. Okay? Everybody's comfortable with stuff like this? So you can ask a lot of questions. I think the next question I want to ask is invertible. When do we have inverses? Well, we always have additive inverses, but we don't always have multiplicative inverses. So it turns out if a and n equals 1. So this means the greatest common divisor of a and n equals 1. Or we might say they're relatively prime. So if A and N are relatively prime, then there's a multiplicative inverse. Then we have a multiplicative inverse. And the way you get this is you get this with the Euclidean algorithm. So the proof is by the Euclidean algorithm. There exists x and y such that xa plus yn equals 1, which is good for you to see. So it's having a little issues in terms of focusing. Okay. So by the Euclidean algorithm, we will be able to get a choice of x and y such that this equals 1. All right. So how does this help us? How does this give us the proof? How does this give us the inverse to A? Yes?
Well, isn't x the inverse of A?
Yes, so x is just the inverse of A. If we look at things mod n, this vanishes. So mod n, we get xa is equivalent to 1 mod n. And so we found an inverse. All right, so then the question becomes, does every number have an inverse? So no matter what I choose for my m and n, will I always be able to find an inverse? What do you think? Did you have a, what do you?
0 never has an inverse.
0 never has an inverse. All right, so we'll throw away 0. That's okay.
And some numbers never.
So let's look at an example. So we'll take n equals 7. So we look at z mod 7z. This would be 0, 1, 2, 3, 4, 5, and 6. We know 0 has no inverse. 1 times 1 is going to go into 1 mod 7. Can you think of anything which multiplies by 2 will get us 1 mod 7? 4. What about 3? What should I multiply 3 by? 5. And then, of course, I also get 4, 5, 6. And now, so I can do 2 times 4. I can do 3 times 5. And now I just need 6. And what is 6? 6 times 6. And these are all equivalent to 1 mod 7. So as long as we stay away from 0, it looks like everything's invertible. Yeah.
Except 7 is prime, so there may be
an
exception.
So the question is this truly a generic number here, 7? Or is this basically somehow related to the fact that 7 is prime? Well, let's look at another one. We could look at, let's say, for example, let's look at z mod 12z. And when you do this, there's no inverses for the following numbers: 2, 3, 4, 6, 8, 9, and 10. Inverses for 1, 5, 7, and 11. I guess there's one more number I should probably write for no inverses. I should probably include 0. Okay. So again, you would just go through the calculation. Is it hard to see that there's no inverse for 3? No, there's only finitely many possible candidates. I can just try them all. Right? So we have at least a brute force way to see that there's no inverses. The brute force way is just try everything. I don't think I played that song for you guys on Monday. No, when Kayla was here for problem solving, we played Try Everything from Zootopia on Monday. But just try everything. There's 12 candidates, they all fail. This is not a good way to proceed in general because as n gets larger and larger and larger, there are more things to try. So here is a proof that 3 inverse mod 12 doesn't exist. assume x times 3 is kind of going to 1 mod 12. That would mean, 3x minus 1 is some multiple of 12. But 3 divides this, and 3 divides this. So this implies that 3x minus m times 12, which equals 1, is a multiple of 3. And 1 is not a multiple of 3. So we see that 3 can't be invertible. And what's nice is this proof generalizes. The key fact was that 3 and the modulus n shared a factor. So we've actually proved a more general result. What we've proven is if a and n are not, what's the lemma, are not relatively prime, then a has no multiplicative inverse. If relatively prime has a multiplicative inverse. And the last part was just the Euclidean algorithm. And this is why the primes are so nice, because the only number that has a common factor with the prime would be 0. Or if you want, p itself. So we often write, z mod nz star to be the invertible elements. So what's nice here is we have both a multiplicative and an additive structure. Okay. How many of you have not seen stuff like this before? Okay. This is one of the challenges when you're teaching a class like this. Abstract algebra is not a prereq, which is good because I've never taken it, but a lot of times people have seen all these calculations before in other classes. If you have not, please speak up or come to my office. It helps to have language to attack problems like this. How many of you have seen the concept of a group? How many of you have not seen the concept of a group? Okay, so I am not going to give the minimal definition of a group. I will give the definition that most people use. So we say a group is a set with a binary operation satisfying the following 4 properties. I will write the binary operation with a star, just because I don't want to specify what it is. So the first is closure. If x and y are in G, then x star y is in G. So you should always be thinking of an example. I could be thinking maybe of the integers under addition. If I take 2 integers and add them, I still have an integer. I could look at z mod nz. If I take 2 integers and I add them, mod 12, I still get something. The next is associativity. X, y, z are in the group. Then x star y star z is x star y star z. And if you think about addition and multiplication are associative. I'm not assuming commutative. Okay? A lot of groups are commutative, but I'm not assuming that. The next is identity. There exists an element E in G such that for all x in G, E star x is x star E is x. There's a do nothing. And then the last is inverse. For all x in G, G, there exists a Y such in G, such that X star Y is Y star X is the identity. Just as a side, for those of you who have seen stuff like this before, you can weaken some of these things so that maybe you're only assuming a left identity and a left inverse. And then you can get the other stuff. When I was taking my generals at Princeton, I was asked, what happens if you have, I think, like a left identity and a right inverse? You know, is that enough to form a group, or could there be some difficulties? What's the minimal set of conditions? For the most part, these conditions are always met. These are a good way of formulating things. So we would like some examples of groups. So examples. The integers under addition. That's going to be a group. If you add two numbers, it's a number. Doesn't matter. You can. Addition is associative. The identity element would be 0, and then the inverse of x would be negative x. You could also do z mod nz under modular addition. What about the integers under multiplication? Is that a group? No. Why not?
There's no multiplicative inverses.
For which elements don't have multiplicative inverses?
2.
2. So if you look at the integers, 2 does not have a multiplicative inverse. So instead of looking at the integers, what should we look at? The rationals. Right? Because now the inverse of 2 is just 1/2. Now it's good. And the inverse of 5 is 1/5. And the inverse of 3/4 would be 4/3. So are the rationals a group under multiplication?
No, because 0.
But that's just one failure. I mean, every other rational works. I mean, how big of a deal is it that there's one exception?
I mean, if you get rid of it.
So we get rid of it. So we look at Q star, which is Q minus 0 under multiplication. That would be a group. So we throw away. Okay. A more interesting group is the Rubik's Cube. So we need to define what we want our group elements to be. So let me just move a little bit closer. Okay. I'm going to say a group element is just a sequence of twists and turns. There's not that many twists. I can twist the top by 1. Is that different than twisting it backwards? Yes. But if I just twist it one way 3 times, that's the same as going the other way once. So I have the twisting move from the top. I have a move over here. I have a move over here in the center. Do I need to consider this move? No, if I have this as a move and this as a move, if I move this down and this down, that's the same as moving this forward. So you could ask, what are your basic moves? And this leads to the notion of a generating set, that I can generate all moves from starting with a simple set of rules. And then closure would be, if I mix up the cube and then do another mix, is that still a move? Hopefully I've not screwed it up too badly. Okay. Right? So does everyone agree a move followed by a move is just a move? Associativity, that doesn't matter which way I group. It's a little bit harder to see, but that's still there. Identity. Oh geez, what would be the identity move?
Nothing.
Okay, good, I can do nothing. What about inverse? I'm sorry? Yeah, just do them in reverse order. So if you remember your matrices from linear algebra, when you take the transpose, you put things in the opposite order. Right? If you want the inverse of A, B, it would be B inverse A inverse. You put things in opposite order. So if I want to do the inverse of this, I do the moves in opposite order. And the opposite of this would be spinning it backwards 3 ways. Okay, so we're all good on that. So this is an example, and you can see that it's a non-commutative group. So if I were to go this and this, that's different than doing this and this. So the order in which I do moves matter. This is a very complicated group. It has a lot of incredible properties. One of my favorites is they call this the God number of the cube. Anybody know what the God number of the cube is?
Is it the furthest away you can get it from being solved in a minimal number of moves?
Yes. So if the supreme being were to show up and you were to give them a cube, this is the number of moves they would need at most to solve the cube. So the God number for the cube is around 20. I think it's actually 20. The Miller number, how many moves I need, is a lot higher than 20. I think I might be somewhere in the hundreds, low hundreds, I think, for the way I know how to solve the cube. Okay? But what this means is that no matter how it's mixed up, you can somehow find an inverse in at most 20 steps. One of the big themes of this class is efficiency. One way is if I give you a sequence of the moves as to how it was done, I can always undo them, but there may be a faster way. There may be some very interesting relationships going on. Okay, so this is basically what a group is. We've talked about examples. We've talked about Z mod and Z star. This is going to be a great group under multiplication. So this is a group under multiplication. Or perhaps maybe it's better to just put it over here with our list of groups. Z mod and Z star. And if you think what we're doing is we're taking a set, and then all the elements that are not multiplicatively invertible, we throw them away. And then we hope that what's left over will be a group. Okay, these are some of the basic building blocks for the investigations in number theory. And you can prove results in abstract algebra about groups. Those results will then apply here. Okay, so now I think the next thing I want to talk about is Fermat's little theorem. So everyone here has seen a proof of Fermat's little theorem? How many of you could prove Fermat's little theorem right now?
I've used my notes.
No notes.
I don't remember exactly what it is.
Okay, so there are two big theorems that we remember Fermat for. And unfortunately, both have the abbreviation FLT. Fermat's little theorem and Fermat's last theorem. So the way I and other people like to write it is F lowercase l capital T for Fermat's little theorem. And here's the claim. If A and P are relatively prime, then A to the P minus 1 is congruent to 1 mod P, or if you want, A to the P is congruent to A mod P. Because A is relatively prime to P, I could divide both sides of this by A. This says that A to the P equals A plus let's see, some multiple of P. So can I go from this to A to the P minus 1 is congruent to 1?
And divide both sides by A.
So can I divide both sides by A? Well, so let's look. I would have A to the P minus A is equal to a multiple of P. Now I factor out an A, and I would get A to the P minus 1 is equal to a multiple of P. We've got to be really careful when we do mod arithmetic, which is why I'm happy to spend a little time doing this. This is a multiple of P. So one of these two terms must be divisible by P, right? It's not A, because we've said A is relatively prime. So since A is relatively prime to P, it's got to be A to the P minus 1 minus 1. So P divides left-hand side. P does not divide A, therefore P divides A to the P minus 1 minus 1. So it takes a little bit of work. But what's really going on here is that if you have a relationship like this, you can do some division. So I'll just do it as a quick aside. So you have AX is congruent to BY mod, is congruent to AY mod P. Then X is congruent to Y mod P if A and P are relatively prime. That you can remove a common factor mod p. So we did the special case of a to the p. What if I just replace that with x and you can see the proof? Do you think this is true if a shares a factor with p, or if we do things more generally? So for instance, let's say we have 4 times 3 is congruent to 4 times 6 mod 12. Is 3 congruent to 4 mod 12 hold? Can I just remove the 4? No, is 3 the same as 4 mod 12? No, so clearly this is failing. What went wrong? That's 12, that's 24, they're both 0 mod 12. What goes wrong is that 4 has a common factor with 12. And that one of the reasons these were equal is that common factor helped me get to 0. I can't remove factors if it has something in common with the modulus. But if it's relatively prime to the modulus, I can then remove it. So this is a really nice property of modular arithmetic. I can just pull out the factor of a from both sides, so long as a is relatively prime to p. Well, we're assuming a is relatively prime to p. If a were not relatively prime to p, is there any chance that this could hold? Say a is relatively prime to p. Could a to the p minus 1 equal 1 mod p? So a is a multiple of p. I'm not going to get a multiple of p being 1 mod p. P divides this. But look at this version. If a is a multiple of p, would this still hold? Yeah, now we get 0 is congruent to 0 mod p. So this is the cover your ass version, the technical term. This will be true in a little bit greater generality. I don't have to worry about a being relatively prime to p. I often want a to be relatively prime to p. I often want to work with this one. But this one I'm a little bit safer. If I forget that condition, everything's fine. Okay? All right, so let's prove Fermat's little theorem. I will do the standard proof. This is the proof that's in the book. I will then also do a more exotic proof that illustrates some nice concepts that we've seen and gives you another perspective. The idea is always to try to figure out why something is true. I can give you a proof, but at the end of the day, does the proof illuminate anything? Have I talked to you about the bet I made in grad school about Morley's theorem? Okay. I actually have this framed in my office as a lesson on how not to live your life. So, Morley's theorem. Take any triangle, trisect the angles. Okay? For each side, look at the 2 trisectors that are closest to it. Those give you 3 points of intersection. Anybody want to conjecture anything about this triangle?
It's equilateral.
It's equilateral. So Morley's theorem is no matter what triangle you start with, you end up with an equilateral triangle. So I was talking with 2 of my friends when I was walking into the math department as a grad student, and this came up one day. I said, oh, the proof's trivial. Really? We don't know any zero. Yeah. You just write down the coordinates of the 3 points of the triangle, calculate the equations of the lines, determine the points of intersections, calculate the squares of the lengths, and show that they're equal. So one of my friends bet me not that I couldn't, but that I wouldn't have the patience to finish the calculation before we got our PhDs. If I can do it, I get dinner not to exceed $12.50. If I can't, I owe him an ice cream not to exceed $2.50. Back then, those were reasonable prices. This was over 20 years ago. It took me about a year and a half to have the patience to finish the calculation. The best angles, the best variables to use is like tangent of 1/3 of the angles. You keep clearing denominators and whatnot. If anybody wants to, I think I have the files somewhere. I end up getting polynomials of degree, I think, 48 and 2 variables for these lengths. I'm allowed to use Mathematica. I expand everything out. And if you have polynomials and 2 variables of finite degree, the only way they can be equal is if they're equal term by term. So you then just subtract. And when the dust settles, you see it's true. and that's a proof of Morley's theorem. I could go through the details, I could write down the equations for you, and my feeling is you would have no understanding of why Morley's theorem is true. You would know the fact, but you would have absolutely no understanding of why it's true. John Conway at Princeton has a beautiful proof where he starts off with an equilateral triangle and reverse engineers to get back the original triangle you're starting with. And you can really see what's going on with that proof. That's a good proof. What I want to do is I want to give you different types of proofs. Different proofs give us different information about the problem. They introduce different functions, different ways of looking at things. And you want to figure out which one is going to generalize, which one will lead to other things. Okay, that's what we really care about. So let's go and let's do a proof. So the first proof of Fermat's little theorem. So we're going to use the factorial function. So n factorial is n minus 1, 3 times 2 times 1. This is the number of ways of arranging n objects with order matters. If you have n people, you have n choices for who's first, then there's n minus 1 people left over, n minus 1 choices for who's second, n minus 2 for who's third, and so on and so on and so on. Think of this as choosing officers for a student government. There is a difference between being president and being vice president, being secretary, being treasurer. The next one is when order doesn't matter. So when order doesn't matter, how many of you have seen binomial coefficients? Is there anybody here who has not seen binomial coefficients? Again, remember from differential equations, if you haven't seen something, odds are someone else has not seen them too. All right, so I'll do it really fast. So if choose k from n and order matters, the number of ways you can do this is n for the first, n minus 1 for the second, all the way down to n minus k minus 1 for the kth. This is the number of ways to choose k people from n when order matters. What does the top kind of look like? What's this beginning to look like?
Factorial.
A factorial. So one of the biggest things we do in mathematics is we rewrite expressions. So how could we rewrite this? Well, this is looking like a factorial. Let's multiply by n minus k factorial. Now, I'm not allowed to just multiply willy-nilly the numerator. So the only way I can do this is I then have to multiply the denominator also by n minus k factorial. So I've just multiplied by 1. So this is the number of ways of choosing k people from n when order matters. You might remember from high school, we might have called this NPK. Anybody remember this notation? Or their calculators might have an NPK button if you still have a calculator. The next question is, I want to choose k from n, order doesn't matter. Well, how many ways are there to arrange k people? K factorial. So if I have k factorial ways to arrange people, then every time I have an unordered set, there are k factorial ways to order it. Another way of looking at it is k factorial sets will have the same people in different orders. They'll all collapse down. So it's called NCK, or we often write it as n choose k like this. And this would be n factorial divided by k factorial n minus k factorial. So now order doesn't matter. Right? So these are some of the most important building blocks. And then someone from the class sent me a really nice one, which is appropriate for Valentine's Day. I factorial divided by u factorial I minus u factorial. I'll let you figure out what that means. All right, so we have these as the fundamental relations. What's nice is the factorial function is recursive. If you know 5 factorial, it's not hard to get 6 factorial. 6 factorial is just 6 times 5 factorial. There's one number, one natural number that we haven't really defined yet. And it's what's 0 factorial. So we need to add 0 factorial equals 1. This is a definition. The best explanation I can give as to why we want to define it this way is n factorial is the number of ways to order n people when order matters. How many ways are there for you to order no one? There's one way for you to do nothing. There's not multiple ways of doing nothing. Later on, if people are interested, maybe we will see that -1/2 factorial equals the square root of pi. There's a way to generalize the factorial function. And it turns out this is an extremely important generalization. It's called the gamma function.
Oh, it means I choose you.
Yes.
That's good.
But you could also do, I guess, I factorial divided by 313 factorial, 313 minus I factorial. That would also work. So the gamma function is defined as the integral from 0 to infinity of e to the minus x, x to the s minus 1 dx. I'm not going to really go into this too much. It turns out that when s is a integer, this is related to the factorial function. Gamma of n plus 1 turns out to be n factorial if n is a non-negative integer. It's often just useful to see, generalizations.
Wouldn't this be I minus 313 factorial?
Oh, sorry, yes, sorry. Fastest way to fix it, thank you. Okay. So now, let's prove Fermat's little theorem. So the first method of proof is the factorial proof. This is probably the most common one you've seen. Sometimes they isolate a result of this as Wilson's theorem. So, proof of FLT. So, A is relatively prime to P. Okay? So consider A times 2A times 3A times ... times P minus 1A. We're going to consider this product. I claim that these numbers are all distinct mod P. So we claim distinct products mod P. And to see this, imagine NA is congruent to MA mod P. Then you would get N minus M A is a multiple of P. But since A is relatively prime to P, this means P divides N minus M. Thus P divides N minus M. But N and M range from 1 to P minus 1. Is there any way that this difference could be a multiple of P? Without loss of generality, we may assume M is less than N. And so the largest N minus M would be P minus 1 minus 1, which is P minus 2. So we would get, and the smallest it could be is if they were next to each other. So we would get 1 is less than or equal to N minus M is less than or equal to P minus 2. So we can't have two different ones of these equal mod P. So do we all agree that these numbers are the same mod P as 1, 2, 3, 4, 5 all the way up to P minus 1? But we can't have two of them being the same, right? So if I want to look at things mod P, and since we're only trying to show that A to the P minus 1 is congruent to 1 mod P, it's natural to look at things mod P. Remember, the goal is to show A to the P minus 1 is congruent to 1 mod P. What this means is when I look at products, I only care about my products up to a multiple of P. So I get A times 2A times 3A ... times P minus 1A is congruent to 1 times 2 times 3 times ... times P minus 1 mod P. Well, now we can group, this is the same as p minus 1 factorial times a to the p minus 1 is congruent to p minus 1 factorial mod p. And we've just shown earlier today that if we have an equivalence like this, we can cancel from both sides so long as it's relatively prime to the modulus. So as p minus 1 factorial is relatively prime to p, we can cancel. Right? So the only way these can be equivalent in 1p, p doesn't divide this p, okay, we get that a to the p minus 1 must be equivalent to 1 mod p. And that's the proof. How many of you have seen this proof before? Okay. And as a nice consequence, or as a nice question, what is p minus 1 factorial equal? Turns out we don't need to know. But there is a very nice value for p minus 1 factorial. And so as a nice exercise, or an extra credit, prove what p minus 1 factorial is. Okay. You ready for the second proof? I think I came up with this proof many years ago. I do not assert that this proof is original to me. I am sure that this proof is in the literature in many, many places. There's just a lot of things that are natural once you try it. And I'm sure I've read this in many places. So we're going to use the following fact. Proof 2. If 1 is less than equal to k is less than equal to p minus 1, then p choose k is a multiple of p. Proof. P choose k is p factorial over k factorial p minus k factorial. What kind of number is p choose k? So what kind of number is this? It's an integer. This is an integer. P can't divide anything in the denominator. P divides the numerator. So this is an integer. P does not divide denominator. P divides the numerator. Therefore, P divides P choose k. And it's very important that we stay away from from k equals 0 or p. P choose 0 is 1, P choose p is 1. And that's the only way, because if your k was 0, we would have a p factorial down there. So that's why we need to stay away from this stuff. Okay. Everybody happy with this claim? I'll now show you how Fermat's little theorem follows from this. Back to FLT. We're going to prove it by induction. So proof by induction. 1 to the p, and what I'm going to do is I'm going to prove a to the p is congruent to a mod p if a and p are relatively prime. And if a and p are relatively prime, I can remove the a, it's not a big deal. So I claim 1 to the p is congruent to 1 mod p. Are we all happy with this? Alright, so now let's look at 1 plus 1 to the p. By the binomial theorem, I can expand this out. So remember, x plus y to the n is the sum of n choose k, x to the k, y to the n minus k. This is the binomial theorem. I just expand things out. If p was 2, it would be x squared plus 2xy plus y squared. If p was 3, it would be x cubed plus 3x squared y plus 3xy squared plus 1. This is Pascal's triangle. So when I expand this out, I'll get 1 to the p plus p choose 1, 1 to the p minus 1 times 1. plus p choose 2, 1 to the p minus 2, 1 squared, plus dot dot dot, plus p choose p minus 1, 1 times 1 to the p minus 1, plus 1 to the p. What do we know about all this stuff over here? What can we conclude about all this junk in the middle? I'm sorry?
Should be all ones.
Not all ones. They're all multiples of p. P choose 1, that's a multiple of p. P choose 2, that's a multiple of p. P choose p minus 1, that's a multiple of p. These are all multiples of p. So this is congruent to 1 to the p plus 1 mod p. What I'm doing is I'm slowly working up. So now we have 2 to the p is going to be 1, well actually, instead of writing that, I could write it as 1 plus 1. And what's 1 plus 1? Also known as 2. So we've now shown 2 to the p is congruent to 2 mod p. I could now replace this 2 with this 1 with a 2, etc., etc., etc. So let's just go by induction. It's nice to see the induction carefully. So we can assume b to the p is congruent to b mod p. I guess we should use n. We can do induction with n. Show true for n plus 1. So n plus 1 to the p is going to be n to the p plus p choose 1 n to the p minus 1 times 1 plus p choose p minus 1 n times 1 to the p minus 1 plus 1 to the p. What do we know about all this gunk in the middle? Multiple of p. And so now we get n plus 1 to the p is equal to n to the p plus 1 mod p. But by the inductive step, what is n to the p congruent to mod p? I'm sorry? N. Excellent. So n plus 1 to the p is congruent to n plus 1 mod p. And this is the inductive step. And so we just march up. And so what we are able to show is a to the p is congruent to a mod p. And then if a is relatively prime, then we can just remove the a and get Fermat's little theorem. So when we're doing all this expansion, we don't need that a is relatively prime to p. We just need that at the very last step when we want to get a to the p minus 1. So this is two different proofs of Fermat's little theorem. Okay? Who cares? Yes, you care. Okay, good. At least one person cares. 2 people care. Okay. Why do we care about Fermat's little theorem? It's nice.
It's nice.
Oh, what a mathematician. It's nice.
And then it's easy to find if a number is prime or not.
Ah, we can use this as a primality test. So how can you test if a number is prime? We actually have a primality test. So we've got about a minute left. That's more than enough time. So this is under the who gives a. Given n, choose a such that a is relatively prime to n. If a to the n minus 1 is not congruent to 1 mod n, then what must be the case? What must be the case?
N is not prime.
N is composite. Then n is composite. I'll assume n is at least 2. Wow! This is an interesting way to find out if a number is prime. So if a number fails this test, it's composite. if it passes this test, is it prime? Not necessarily, maybe. So then the idea is, if it passes the test, do it for a lot of different choices of A. Every time it passes, you become more and more confident. So then the question is, 1, if you pass it for every A, must you be prime? And B, how difficult is it to actually calculate A to the n minus 1? One of the themes of this class is efficiency. Just because I write this, my n might be of size 10 to the 200. I don't necessarily want to raise A to the 10 to the 200th power. That is a little bit beyond what I'd like to do. So is this practical? So we will talk about that on Monday as we continue with all the stuff here. But this actually gives you an idea of, here's a basic result. We're still in week 2, essentially, of the course. And we've got a test for primality. That's not bad.
Yeah, Fermat is not bad.
No.